right? I thought there'd be data. Is anyone out there?
Okay, welcome back. How is the homework going? Any questions on anything? Yeah, so I couldn't open Canvas on this computer that I'm using, so I have to look at the homework on another computer. That's why I'm looking over there. Yeah, there is no proof. It's just so. Okay, so for 4B, the point was to kind of just draw a number line and put a fixed value of little xk, and then the way the kth order statistic could equal that value would mean that of your random sample, you need one to fall right here. So 1x, which yes, is going to happen with probability 0, but that's why you're not doing the formal proof, which I'm going to hand out. I have a order stats handout when this homework's done. But the idea is you kind of want one there, and then you want k minus 1 here. So you want k minus 1 of the x's over here, and then you want n minus k of the x's over here. And then the quote unquote probability that one of the x's falls right here on xk is f of xk. Now that's a PDF, so the probability of falling there is 0. But this is why I was talking about a heuristic kind of, if you treat it like probability, then the probability of getting 1 right here is equal to this. And then the probability that any one of these guys is down here is going to be the probability that just any x is below xk, and that is f of xk. And the probability that any one is up here, that's the probability that an xi is greater than xk, and that is 1 minus f of xk. So you can see from the problem that you have k minus 1 down here. So you're going to get this guy k minus 1 times, and you have n minus k up here, so you're going to get this guy n minus k times. And you're almost there, but you just sort of have to count the ways these can fall. And to give you a hint on the coefficient, there are n factorial different ways to spread these numbers out. And some of them are redundant, because if you take your sample of size n and they fall maybe here, then if you mix these up, like start switching these around, it's not going to change the overall result of having the, in this case, 4th largest one fall right here. So all of the yellow x's, there's supposed to be n of them. There's n factorial ways to spread them out, but these 3 x's, there's 3 factorial ways to move those around that won't change anything. So you're dividing out kind of redundant stuff. But yeah, it's not a proof, it's just sort of talk through it. Other questions? You could start with the normal moment generating function from the table, and then compute the moment generating function for this, and then find the result in the table. I think that's going to be a completing the square problem kind of thing. Could be wrong. Does anyone else want to talk in more detail about that one? This is number 6 on the homework, and we're trying to take a normal 0, 1 random variable, and we want to show that x squared has this chi-squared distribution with parameter 1, and that has been defined for you as gamma of 1/2, 1/2, because in the problem we're defining the chi-squared n, and that's a gamma n over 2, comma 1/2. So we know the moment generating function for x. So for the normal, it's e to the mu t plus 1/2 sigma squared t squared. I don't know if I finished that last time we were doing it, I think. Grab it out of the table. So when the mean is 0 and the variance is 1, we get e to the 1/2 t squared. And then for this problem, I'm going to let y be x squared. And I was saying in the hints to the problem that I never think of moment generating functions to find distributions of things squared. It's usually not a convenient way to go, but it is in this problem. So that's why I gave you the hint, because I don't think there's any sort of natural reason you would use moment generating functions to do this. So the moment generating function for y is the expected value of e to the t y. And all I know about y is that it's x squared. So this is the expected value of e to the t x squared. And this is a function of x. So I'm going to put it with a lowercase x in front of the PDF for x, which is 1 over the square root of 2 pi e to the minus 1/2 x squared dx. And x for the normal goes everywhere from minus infinity up to infinity. Actually, you don't have to complete the square here, now that I look at this. There's no completing the square. So we're almost done. I'm going to write one more thing and then leave you to write just one more thing. This is 1 over the square root of 2 pi. I'm going to combine these guys, e. So I'm looking like to integrate without integrating and see a normal kind of thing there because I see the e and the x squareds. So I could write this as e to the minus 1/2. 1 minus 2t x squared. So the reason I forced it into that form is because I have this minus 1/2, which always appears in the normal distribution there, and I have the x squared, and then I have this other thing. So this appears to be e to the, so this is like e to the minus 1 over 2 sigma squared x squared, for sigma squared chosen to be what it needs to be. So if you define 1 over sigma squared to equal 1 minus 2t, then you almost have a normal PDF here with still mean 0 because the x squared is still x minus 0 squared. But we have an actual variance, but we don't have it in here. So you have to put it in here and then compensate and then say the thing integrates to 1. So I know I made this really messy, but I kind of did that on purpose. I know I'm always making things messy, and it's usually not on purpose, but the problem is almost finished. So I want you to find the pieces and put them together. Because basically, once you realize that this is the moment generating function, you want to sort of combine the e stuff and make it look like another normal distribution and integrate without integrating, and the result should match the moment generating function for the gamma 1/2 1/2 in the table. Other questions?
Speaking of things being messy, I was curious about number 3. I felt like I understood what the problem was asking us to do, and then I got to a point where I had this long expression that I was having a hard time simplifying, and it just looked very messy.
It's going to be messy in the middle. I think it simplifies to something pretty nice, though. Yeah, so on 3, we were trying to get the joint PDF for a min and max of a distribution. And I gave a hint and then talked about last time why this hint is true. So basically, I expanded this event to include the 2 events where the minimum is less than or equal to x, or the minimum is greater than x. And this is what we're trying to find. And this guy is saying that the max of all the values is less than some number y. So that's going to be the same as saying each and every one of them is less than or equal to the number y. And so this is going to be the probability that every one of them is less than or equal to y. I'm sure you did this and it just maybe looked, I just don't think it's that messy, but because these are IID, you get to break those up because they're identical. Part of IID, this is f of y to the n And then this guy over here, if you drew a picture for this guy, and I would say, like, suppose, just to be thorough, I would say suppose x is greater than y, then this probability is 0 because you can't have the minimum greater than a number and the maximum less than a smaller number. So in the case that x is less than y, then this event here says the minimum is above x and the max is below y, and that says they're all in here. And so this, more messiness, but this is the probability that every one of them is between 0 of x and y. And then because they're independent, you get to break that up. And then each one of these is the CDF for any one of the x's at y minus the CDF at x, and those are all the same. I don't know, I don't think it's that bad. So to finish it off, to find this, you would take this minus this and take the derivative with respect to x and y to get down to the joint PDF. Okay, so last time we were starting to not really estimate, but determine good qualities of estimators so that when we're trying to estimate parameters, we know what to aim for. And so we have that theta is our generic parameter, and theta hat, which is some function of x1 through xn, is going to be an estimator of theta. And so this guy is a random variable, and this guy is a constant. And if the expected value of this random variable is equal to the constant, we say it's an unbiased estimator. Or more casually, we say that theta hat is unbiased for theta. And if theta hat is unbiased for theta, then the variance of this random variable theta hat is the expected value of the random variable theta hat minus its mean, which is theta, because we're in the unbiased case, squared. But if theta hat is not unbiased, so is biased, not unbiased is kind of weird, is a biased estimator for theta, then this same quantity is still kind of interesting because this theta hat is our estimator, and this theta is the thing we're trying to estimate, and we would like to look at that kind of distance between them. But in this case, it's not the variance, it's called the MSE, or mean squared error. So we define the mean squared error for theta hat to be this thing. And from the line above, sometimes mean squared error is just a variance. And I very often make problems on homeworks and exams where I say, like, find an estimator of this, now find the variance, then part C, find the MSE. But the estimator was unbiased, so there's no extra work to do. So watch for that. If you have to find a variance and an MSE, and it's an unbiased estimator, then you only have to do one of those two things. But if it's biased, we can still relate the MSE to the variance, and I think that's where we were. So, so this is going to be a relationship between variance and mean squared error that will hold in general, even in the biased, or even in the unbiased case. So I'm going to start, I think sometimes I start on one side. Okay, I'm going to start with the variance of theta hat. This is the expected value of theta hat minus its mean, so the expected value of theta hat squared. That's how you define a variance if this is the random variable and this is its mean. So I'm going to do a little give and take here. I'm going to rewrite this as the expected value of theta hat minus theta plus theta minus the expected value of theta hat, and square that whole thing. And so now I'm going to square this out, but I'm going to kind of keep these guys grouped together and these guys. Actually, before doing that, this guy over here is the negative of the bias term that we defined last time. So this is the expected value of theta hat minus theta minus the bias for the estimator, theta hat. So recall that the bias is defined as the expected value of theta hat minus the thing you're trying to estimate. Okay, so now I'm gonna square this guy out, but I am gonna leave the theta hat and the theta group together. And so using the linear operator property, I'm also gonna run the expectation through. So I'm gonna get the expected value of theta hat minus theta squared minus 2. So one thing I want to point out is that this bias is an expected value, which is a constant, minus the unknown parameter, which is a constant. So bias is constant. So when I run the expectation through, I can pull this out. And then the final term is going to be the bias. Someone who doesn't like to break the board like this. This is awful, writing on both of them at the same time. This is the bias squared. Again, bias is not random. So stop me if that doesn't make sense. But this guy, if you run the expectation through, you get the expected value of theta hat minus just theta, because that's a constant. So you get the bias again. And so overall, this guy is the MSE for theta hat. And so what we have shown, here is the punchline, the variance for theta hat is the mean squared error for theta hat minus a single bias squared, because I have minus 2 of them over here and plus 1 of them over here. So that is in general the relationship between variance and MSE. And of course, as we already saw, if we have an unbiased estimator, then this bias is 0 and the variance is the same as the MSE. Let's estimate something. Let's make some guesses and see if we have guessed well. Okay, so this is just an example overall of estimation and unbiasedness and variance and MSE. So I'm going to take a random sample x1 through xn, IID exponential with rate lambda. And first thing I want, stepping stones here, is I want to find an unbiased estimator, not for lambda, we're going to get there, but for a function of lambda, which we're using tau to denote our functions. So of tau of lambda, which is going to be defined as 1 over lambda. That's just, there's no why, that's just the question. It's a building block to something else. So you probably recognize 1 over lambda as the mean of the distribution. And we saw last time that x bar, the sample mean, which is 1 over n times the sum, is always unbiased for the mean. It's always unbiased for what we were calling mu, but that's supposed to be a generic mean in this case, the expected value of x1 or x5 or any of them, which is 1 over lambda. So we can take as our estimator for tau of lambda, we can take this to be x bar. We've got now an unbiased estimator of 1 over lambda. I think you're probably more interested in lambda, and we're getting there, but no work at all if you recall that x bar is always unbiased, for the mean. Okay, so if you ever give an estimator, you usually want to give the variance as kind of a measure of spread. When we get further in this course, we're going to do things like confidence intervals, which is rather than give a point as an estimator, we're going to do a little plus or minus and have some feelings about it, like we're confident. So this is said to be a point estimate. Well, once the number is computed. This is an unbiased estimator. Okay, but what I'm trying to say very poorly is that we care about the variance of our estimators. So part 2, let's find the variance of the estimator from part 1. So tau of lambda hat. And don't make too much work out of this. The variance of tau of lambda hat is the variance of x bar, and we showed last time that this is sigma squared over n, and sigma squared represents the variance of any one of them. So for the exponential distribution, if you check out the variance column, the sigma squared is 1 over lambda squared. Okay, so let's do something more interesting. Let's find, here's where it's at. Let's find an unbiased estimator of lambda itself. Okay, so we have that x bar is an unbiased estimator for 1 over lambda. So motivated by that, I'm going to try looking at 1 over x bar. Now, that should not be right because the expected value, let me put this as a note, the expected value of 1 over x bar is in no way, shape, or form equal to 1 over the expected value of x bar, because integrals just don't work like that. You know, this is just in general, if you're computing like a 1 over some x times a PDF, this is not the same thing as 1 over the integral of x times the PDF. So no way. But motivated by that, let's take a look at the expected, oh, by the way, if that were true, then we'd have 1 over lambda, and we'd have lambda. So motivated by that, let's just check this out anyway. So let's investigate. Okay, so that's a lot of what's coming up. You are going to make a guess, and then if we compute this expectation and we see something that is like a function of lambda where we can easily move things around in order to get an estimator that will give us lambda, then we're done. Okay, so the expected value of 1 over x bar is equal to the expected value of n over the sum of the xi. And I can pull the n out, and I'm going to call that sum 1 over y, where y is the sum as I goes from 1 to n of the xi. Now we already know using moment generating functions that this is a new random variable that has a gamma distribution, and the first parameter is the number of exponentials we added together, and the second parameter matches that of the exponential. And you already did this expectation on homework 1 or 2. So the expected value of, just do it again really quickly, you do have to assume that, no, I don't have to assume anything. You do have to assume that the sample size is large enough. I'll get to that. This is n times the expected value of 1 over y. This is n times the integral from 0 to infinity of 1 over y times the gamma PDF, which is 1 over gamma of n, lambda to the n, y to the n minus 1, e to the minus lambda y dy. And then we're going to suck this 1 over y into there and make it look like another gamma integral and integrate without integrating. So I have n, the integral 0 to infinity, 1 over gamma of n, lambda to the n, y to the n minus 2. And then if you just look at the y part and ignore the constants, this looks like a gamma n minus 1 lambda PDF. Usually the alpha for the gamma, we see x to the alpha minus 1. And this is only going to make sense if n is greater than or equal to 2. So that is a restriction I should have put at the beginning of the problem. If n is not greater than or equal to 2, this whole thing is just going to blow up. This expectation is infinite. Okay, so if it's like that, then let's make it into that. I'm going to pull out, so I've got my n out front, I've got the gamma of n, I'm going to pull out a single lambda so that I'm left with n minus 1 of them in here. And then I'm going to leave a little more space, 0 to infinity. I'm going to need 1 over gamma of n minus 1. So that means I need to multiply by gamma of n minus 1. And lambda to the n minus 1, y to the n minus 2, blah, 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 blah. Okay, so this actually is the gamma n minus 1 lambda PDF, and that will integrate to 1. And so we have n gamma n minus 1 over gamma of n lambda. So if you're doing this on like an exam or something and you can't remember what gamma is, I'll come back to that. We know what gamma is. Two ways to simplify this. One is that these are integers, so gamma of n is n minus 1 factorial, or our more general way to simplify gamma of n is that it's equal to n minus 1 gamma of n minus 1. So we get n over n minus 1 lambda. So we're looking for an unbiased estimator for lambda, and we don't quite have lambda, but this came from the expected value of 1 over x bar. So let me just sum that up here. Expected value of 1 over x bar is n over n minus 1 lambda. So if you multiply both sides by n minus 1 over n, then you can get the lambda. And if you bring this inside the expectation, and I'm going to go ahead and cancel here. This n will cancel with the 1 over n if you rewrote that as a sum. This tells us that, so I've got an estimator, so I'm going to put a hat on it. Lambda hat, I'm going to define to be n minus 1 over the sum as I goes from 1 to n of the x's. This is unbiased for lambda. So the basic strategy, I'm going to scroll back up. I wanted an unbiased estimator for lambda. Let me put it a different way. The kinds of problems you're going to see before we know how to estimate is to find an unbiased estimator for theta based on a given statistic. And so in this case, we're basing it on x bar. And the first thing you do is note that the expected value of x bar is 1 over lambda. So motivated by that, you're going to try the expected value of 1 over x bar, which is not 1 over the expected value of x bar, but you're going to try. And then you go through it, and if you see lambda in the numerator like this and a constant, then you can adjust the constants. So this is our final answer for n unbiased estimator for lambda based on the sample mean. While we're here, let me rename this estimator to be, so let me get a color here. Oh, I can't see that. Lambda 1. So I'm going to rename this because I want us to come up with another unbiased estimator for lambda based on what we know so far in this course. So this would be 4 in the list. Let's find another that's more than I wanted to get into, sorry. Let me just cop out here. I'm going to just call that lambda hat. And let's find another unbiased estimator for, I'm going to go back to 1 over lambda just to make a simple example in our first example. We have one, it is x bar, but we want to find another one based on the minimum value in the sample. The whole point of most of this course is to compare estimators and come up with the best one. The umvu. We're not there yet, but we will be close to Thanksgiving. Okay, so to find an unbiased estimator for 1 over lambda based on this guy, I would start by finding the expected value of this guy and seeing if I can manipulate it. I'm going to start with trying the expected value of the minimum. So recall that we found the distribution of the minimum, and if you don't recall it, or if we hadn't done it, at this point you would want to find the distribution of the minimum. We did this and we got that the distribution of the minimum is exponential with rate n lambda. So the expected value of the minimum is 1 over n lambda, because that's how exponential means relate to the rates. I wanted 1 over lambda, so I'm going to move the n to the other side. And so I've got the expected value of n times the minimum gives me 1 over lambda, which means we have an unbiased estimator of 1 over lambda. So 2 unbiased estimators of tau of lambda, which was defined to be 1 over lambda, are tau 1 lambda hat, which is x bar. We found that way back at the beginning, step 1 here. And now we have a second one, tau 2 lambda. That's a little weird, huh? It's an estimator of tau, so it's like it's our first estimator. You could actually write things as I did, but I'm going to write it that way. So I've got a tau 1 hat of lambda and tau 2 hat of lambda, which is n times the minimum. Really, what this is denoting is the tau that has been estimated. And like I have the first one. That's awful. So if you're really trying to estimate lambda, which one of these would you choose? I'm sorry, 1 over lambda. Which one of these would you choose? You would then go and compute I'm going to spare you this. You would compute the variance of this guy, which is easy and fast because of our general property of variances of sample means. And you would compute the variance of this guy, which is not bad at all because you would pull out the constant and it would come out squared, and then you would compute the variance of the minimum based on knowing that that has an exponential rate and lambda distribution. So you can just look that up in the table and you can compare the variances. And I would say out of these 2 unbiased estimators, I want the one with the smallest variance. Okay. I suppose I was supposed to do an MSE. This is just kind of busy work at this point. Let's do one. Let's see. Sorry for the scrolling. I'm going to go back to the unbiased estimator for lambda and find its variance. Actually, I'm not even going to finish the problem. So if this is 5, let's find the variance. This problem is pretty disjointed. All these pieces are just different calculations for our unbiased estimator of lambda hat. So to start this, I won't drag you through the whole thing. I would write out what lambda hat actually is. This is lambda hat, and this is the variance of n minus 1 over the sum of the x's. And you can pull out that constant, but they come out squared. And we can treat that sum of the x's as a new random variable y that has the gamma distribution. By the way, we don't have to pull out any of these coefficients. I'm going to scroll. I wrote, originally when I wanted to compute this expectation of 1 over x bar, I wrote it as the expectation of n over the sum of the x's because I know that the sum of the x's has this gamma distribution. We've shown that the sum of exponentials is gamma. But we've also shown that like a constant times a gamma is another gamma. So in fact, you know what, I'm not going to do it. It's just another way. In fact, this whole thing has another gamma distribution. So we could have used that PDF and not taken this out. I'll write specifically what it is. It is n over the sum of the x's. Oh, actually, 1 over that does not have the gamma distribution. So the y is what I'm trying to say. If I define like y tilde to be 1 over ny, then that is going to have a gamma distribution with, so the y being the sum of n exponentials with rate lambda is going to have a gamma distribution with parameters n and lambda. And when you multiply a gamma times a constant, it ends up underneath the second parameter of the gamma. So n lambda, which comes from lambda over 1 over n. That was a mess to just start saying that in the middle of the problem. Don't worry about it. Just for those of you who have observed that it's possible to write this whole thing as a gamma rather than take the n out and write the remainder part as a gamma. This is where I say questions, but I'm not sure I want to know at this point because I'm doing such a bad job of explaining this. Okay, questions?
Actually, I have a quick question.
Yeah.
If you have two unbiased estimators, and one of them has a smaller variance, is there ever a need for the one with the bigger variance, or
no?
Like...
Yeah, I would automatically throw that one out, unless, of course, you have to do further calculations, and for some reason your first estimator is just not tractable to do them. But
okay.
I don't actually ever see that happening.
Cool. Thanks.
Yeah, so back to 5, I would just write the next line and not drag you through it. This is n minus 1 squared, and then this guy can be written as the expected value of 1 over y squared minus the expected value of 1 over y, all squared. And this expected value is done. And this expected value is just the integral 0 to infinity 1 over y squared times the gamma PDF that y has. The y is a gamma distribution. Y to the n minus 1 e to the minus lambda y dy. It's exactly what we did before, but before we had just a y there. But yeah, I would suck that 1 over y squared into this and rewrite it as a gamma. I don't know if I worked this out somewhere. No. You want to do it? It's just now kind of busy work. I think I'll push past it. Cool. Class ends in 12 minutes. I'm on it today. Okay.
Wasn't it wait, is it a minute 40?
Wait, what? Oh my God. Dang it. All right. Just as a teaser, the very next thing that's coming up is the very next thing that's coming up is We want to start, okay, so we're looking at properties of estimators, and we'd like our estimator to be unbiased if possible. We'd like it to be small variance, maybe uniformly smaller than all other variances of all unbiased estimators, which is coming. But the next property for now is we would like it to have good large sample properties. So we're going to talk about convergences of sequences of random variables. And there are many, many ways to define convergence. As I mentioned before, they have to involve probability somehow because we have random variables. So a really, don't write this down, but a really like weak form of convergence is to say that like a sequence converges to a constant in mean, which would mean that the limit as n goes to infinity. This is so weak, we're not even going to use it. Like that's constants, and that could converge in the sense of convergence of numbers. So our first type of convergence is convergence in probability. Next time on mathematical statistics. Thank you.